Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello, my name is Martin Schroeder, and in this lesson we're going to cover the factory pattern. The factory pattern is designed for cases where you need to create objects either on startup or you need to create objects in a predefined way, for example, from data structures. So let's say you have your device tree and you need to create your driver structure, and that is a typical case of the factory pattern. Now, there's multiple ways of implement this pattern, especially in C, and we're going to cover those ways in this lesson. So what are some of the defining characteristics of the factory pattern? How do we identify that we need to use the factory pattern or that it's already being used? So one thing to look at is what objects are being created. So are we creating a device data structure? Are we constructing a visual representation of a web page? Are we constructing, are we allocating some memory areas or memory buffers? Those are typical things that usually warrant using the factory pattern. Next question is, how is the memory allocated? So are we keeping a static buffer of objects where we just return the next free object? Are we using dynamic memory allocation? Are we using a list of objects that keeps track of the allocated objects and free objects? And in fact, if you're developing embedded systems, you can implement object allocation in this way, where you have a static array and then you have a list of free and a list of allocated objects, and then you just remove one element from the free list and construct it. That will be your factory method, and then you put it. Then you return that object, and when that object is deallocated, you return it back to the free list. Next question is, how do we store and pass the creation parameters? One defining feature of the factory pattern is that objects are created from parameters. So if you look at, for example, the device tree definitions for devices, you can look at those parameters for the device, and then you can construct the object. And if we're coding in Zephyr, we would have the entry point to the initialization function, and that entry point would be placed in a specific section of the executable, and then a factory method that is part of Zephyr is going to execute all of the initialization methods, and those initialization method would be the actual construction method for each driver that is part of the system. But we're still creating those objects from a data definition of what needs to be created. Decoupled implementation details. So do we need to decouple the creation of an object from the code that is actually using the object? Does the code that uses the object need to even know about the parameters that are used to create the object? If that is the case, if it doesn't need to know that, then that is one of the key elements that would signal to you that you should implement this using the factory pattern. And then also, what code accesses and uses the factory? Sometimes the factory pattern is implemented very transparently, so the user code doesn't even need to worry about it. And this is the case with device driver initialization in Zephyr, and also with automatic init functions, which are executed before you even enter into the main application. So then to the user, it looks like basically everything just magically initializes, but from the code perspective, we're actually implementing this using the factory pattern. So let's look at some pros and cons of the factory pattern. Or actually, first, let's look at use cases for the factory pattern. One use case is instantiation of device driver data, such as with the macros device define, memory pools and buffer pools. So when you need to allocate connections, for example, for Bluetooth interface, network device creation macros, which are kind of similar to device creation macros, but they're used for the network interfaces. File system objects, if you use fopen on Linux and it returns a file structure, that's a typical example of the factory pattern at work, where the fopen function actually constructs that structure for you based on the file name that you've provided. Network socket, network packet creation and protocol buffer packing. So if you use protobuf, for example, then it generates the factory methods for the different protocol buffers. So you just pass them the input data, the contents of the message, and then it packs that message into a protocol buffer that you can then send over a connection to another device. And that is also an implementation of the factory pattern. So what are the pros of using the factory pattern? Increased flexibility is one benefit of using the factory pattern, because you're parameterizing the creation of the objects. For example, with the device tree, when you can construct the devices based on a data representation, it becomes much more flexible than having to have functions for setting each one of the parameters. So we have a data-driven object creation, and data-driven design is more flexible, but then on the other hand, it's also harder to test, because you have more data. You have more data variations to test, and the behavior of your code is going to depend on the data rather than on the code itself. So it can be a little bit harder to test, but one of the pros is that it gravitates towards data-driven design. Improved testability sometimes, so not always, but sometimes we get better testability because our user code becomes very standardized. For example, as with the file fopen function, there's just so much going on underneath the fopen function. It needs to call the operating system, it needs to open the file, it needs to manage the inode structure, or it doesn't manage the inode structure, but it needs to do a lot of work underneath, and all of that work is hidden from the user code. So testing the user code becomes much simpler. We just need to test that the user code passes the correct parameters to the fopen function, and then we can assume that if the fopen function does its job, then the user code will get a file handle that it needs in order to access the file. So the testability is improved as a consequence of having a very limited and well-defined API. And it's always the case, that's always going to be the case, but the factory pattern kind of forces you to have a very well-defined API, because it's kind of the side effect of implementing the factory pattern. Improved code reuse. So as a consequence also of the standardized API, you get improved reusability of the code, because your code does not contain the creation parameters. It just contains calls to this API. So moving the code to a different implementation that perhaps has a different way of creating objects, it would be very easy, because you wouldn't need to modify the logic of your code. And also improved scalability. So when your code doesn't need to know about the creation parameters, you can have a lot of objects that use the same API for creating an object, and then you can have multiple implementations of the creation method. So let's say if we go back to the file system example, we can have a file on the X4 file system, on the RazorFS, on the X2 file system, or FATFS, and all of those files will be still accessible using the same API for creating the file handle object. So we can then have different applications that use this API, and we can easily scale the number of applications, and then we can also scale the number of implementations of the file systems that we are using. And because everything is kind of going through this single point of the fopen function, the factory method, and has many different implementations on both sides, we have a very high scalability there, because if we add a new file system, we don't need to modify any application code. And if we modify the application code, we don't need to modify any implementation of the file system structures. So in this way, factory method adds a lot of flexibility to the code. Now let's look at the implementation of the factory pattern. So we're going to look at simple factory. We're going to look at embedded factory, abstract factory, and prototype factory, and pooled factory. And this is just different variations of implementing basically the same concept. We're trying to construct objects, and we're trying to simplify the application code by moving the construction of the object into a dedicated set of methods. So let's look at this. So first, let's look at simple factory. So this is the most simple parameterized object creation. And in C, you would implement it like this. So you have your enum, which defines different shape types. You have your shape API, which is an abstract API for the shape. Then we define a generic shape handle, which we define as a pointer to the shape API structure. And there is a reason for this. The reason I do it this way is because I want to save memory by not having to duplicate the API structure itself for every object that is being created. And this is not just some dumb, C optimization in this case, but consider if you have thousands of objects and you have several pointers in this shape API structure, you don't want to duplicate those pointers across every single object, because there's going to be a lot of waste. So we just keep a single pointer in the shape structure, which is in this case const struct shape API. So that's a single pointer to the API, and the handle to the shape is a pointer to that pointer. So what that gives us is the ability to then retrieve the original shape, the pointer to the original shape structure. This is a standard pattern that I use a lot. For type safe, basically type safe polymorphism in C, you could say. So then we have our shape create, which creates the shape, and shape draw, which just calls the API. So we have a API with a draw method here, and this method is going to be different depending on which shape we're creating, whether it's circle or square. So let's look at the next piece of code here. This is the data structures in the implementation itself. So the previous one was the header file. Now we're going to the C file. And then we have two different shape implementations. So we have our shape circle and shape rectangle. And we don't want, so this is kind of the whole point of the factory pattern. We want to keep the implementations away from the application. We don't want the application to have to deal with the different types of objects and different implementations. So we want the application to just call our shape draw function regardless of how many shapes there are. We want to be able to add shapes. We want to be able to change the implementation. We want to be able to change the internal data structures of the shape. And we don't want to have to even recompile the applications. So that's why we use the factory method here to simplify this API so that the application just needs to pass the handle. And so we have two different shapes, and each shape also embeds the generic shape structure, which also then embeds the API. So our shape is kind of the base object, and then those two structures are inherited from the shape structure. And then we have our API implementation. So in this case, we have the circle, where we have our circle draw function, and this is how we retrieve the pointer to the shape circle. So recall we have our shape circle here, and then it contains the shape, and the shape contains in turn the API, the API pointer here. So what we get here in our draw method is the pointer to this pointer to the API, which is our handle, right? So then we use container of, and we say that we want to take this handle here, and we want to get the container of that handle, so the enclosing data structure, and then we pass the pointer to which enclosing data structure we want to get the handle to, or the pointer to. So we have the struct shape circle in this case, and then inside shape circle there is a shape dot API. So the shape is the base class, and then the API is the API pointer to which represents this, which is represented by this handle, right? And so when we do this, we get the shape circle, and then we can do the specific implementation of the join method for the circle. So once you learn this, it's really, really simple. It's only complex when you just start with it, and when you just look at this container off and you think, oh, what is this actually doing? How does this work? But when you get into when you understand how this works, it's actually very, very simple. And then we define our shape API. So this is going to be defined once for all the instances of the shape. And this is actually how C++ does it as well. So there's only one copy of the V table. So we have our shape API, and we then also assign the draw method, or this is kind of like a virtual method, but in C. And we set this to our circle draw method. And then we have our circle init function that takes a shape circle pointer and then just initializes it with the API for drawing a circle. Now we can also implement a rectangle, and we will do this in exactly the same way, but just we have a different draw method, and we have also rectangle in it instead. So now we have two different shapes, and we have circle in it and rectangle in it. And now we can implement the factory. So we have a shape create, and shape create is parameterized by our enum, which is either a circle or rectangle, but more shape types can be added very easily without then having to worry about the implementation of the applications that are using this code. So we have our enum shape circle. We then instantiate a circle structure, and we initialize the circle, and then we return the handle. So in this case, shape T, and that is the pointer to the API of the shape. And then we have our generic shape draw method, which simply calls the API. So the way that we implement this is we take a handle, and we then call, because shape is a pointer to the API structure, so we dereference it so that we get a pointer to the API structure. So this would be the same as API, and then we are calling the draw method, which has been assigned to a different function depending on what kind of shape it is, and then we pass it the pointer to the API so that it can retrieve the enclosing data structure. So that it has access basically to its private data structures. And that's it. So then when we want to use this in an application, we would do like this. We would call shape create, shape rectangle, and then shape create, shape circle. And then we will draw the shape by simply calling the draw method. And this is kind of the whole point of the factory pattern. We're trying to simplify the application. So we don't need to worry about neither allocating the objects, neither the specifics of the creation process. We just simplify it like this so that we can create shapes and then draw them. So next type of factory is the embedded factory, and I call this the embedded factory. You're probably not going to find this anywhere else. This is a name for it that I've just created because I think that this is a pattern that is very commonly used in embedded systems when you need to create objects before the main application runs, but it's not used as often in other places unless you use C++, in which case this is the pattern that is used automatically by the C++ compiler to call the constructors of your static and global variables. But that is a process that's completely transparent to you, so you're not actually thinking about it. But if we're coding on Zephyr, this pattern is used for every single device driver. And what is happening here is that you have a macro called device.dt instDefine. And what this macro does is it takes a few parameters. First of all, it takes the initialization function, which in this case is uart_stm32init. And this is kind of similar to our draw method. It's a particular implementation for creating this particular driver. So what this macro does is it's going to place a pointer in a specific section of the executable itself, which has a specific name, which is defined by Zephyr, where Zephyr then, where the startup code for Zephyr then looks and runs every single function in that list. So when we do it this way, if you care to understand exactly how this is implemented, you can look at the definition of this macros. There's a lot of there's a lot going on here, but the basic concept is very simple. You're placing a pointer into a table, and then the startup code executes every single function in that table. But essentially what you're doing here is you're creating a driver, and then this driver is created from the parameters in the device tree. So that's the data definition of the object that's being created. And the driver code itself completely hides those details from the application. So the application then when the application starts, all of these objects have already been created. So the only thing the application needs to do is basically just get a handle to that device, and then the application can start using it. And that's also the simplification that the factory pattern is actively creating. So factory pattern is very good when you need to simplify the creation of objects for your application. So you don't need to worry about it. In case of C++, C++ will also do this, and it will place a little bit more data into this startup table, where it has the pointer to the object, and it has the constructor for that object that needs to be called. And then the startup code is going to call all of these constructors. And if you've ever used C++ on bare metal systems, you know that you need to do this manually on a bare metal system. You need to actually call the GCC function that does this, that goes through this list and calls all of the constructors. But the concept is basically the same. And this is embedded into the executable. So that could be another way of also relating to the name embedded factory. It's often very hidden and just handled by the startup code before your application even starts. So the next variation of this is the abstract factory. And the basic idea with the abstract factory is that instead of having the abstract objects like we looked in the shapes example, where we had multiple shapes and they were kind of abstract data type. We had an abstract data type shape, and then we had multiple implementations of that shape. We can do the same for the factories, and we can actually make our factory an abstract data type. So this is what the abstract factory is all about. So we can have several different factories that create different colors of objects, different colors of shapes, for example. And then we can have a single API to that factory that creates a shape based on, let's say, we want to make sure all of our shapes are yellow. Then we create a factory that creates only yellow shapes, and then all of our application code just worries about the abstract factory creation method that doesn't care about what color it is. But if we have created the yellow factory in the beginning, then the application will only be creating yellow objects, but it doesn't need to know about the fact that it's creating only yellow object. It will just call the creation method. And that's the concept of the abstract factory. So we just create a factory here. We have the same concept with the API. We have our factory yellow in it. And then we have our creation method, which is in this case a virtual method. And then it can create a circle, it can create a rectangle, and this will basically create a yellow circle and yellow rectangle. And then we have our factory init method and the factory creation API. Then we'll just create a factory, and we will have a factory handle, and then we call a factory create shape, and then from this factory we create a circle, and all of these circles are going to be yellow. And if we create a rectangle, all of those rectangles are going to be yellow. And then we use the same virtual method for drawing the shape itself. So in this way we have a further simplification. And whether you need to use this or not, it would depend obviously on your use case. But if you have the requirement that you need to have multiple implementations of the factory, then you can simplify your application code further by making sure that your factory is an abstract factory. Another way of implementing the factory would be a prototype factory. And the key idea behind the prototype factory is that we're creating objects by copying an existing object. So let's say some object takes a long time to create. The thing that I can come up with is basically like, let's say we have a 3D shape or a 3D world that is loaded from disk. It takes a long time to load it. And once it's loaded from disk and everything is created, we just want to duplicate it. So we have a factory method that simply duplicates that already created object, and that is usually much faster than having to create the object from scratch. So the prototype factory is an optimization for object creation when the object needs to be, when it's time consuming basically to create the object. And we implement it the same way as we did before. And basically the concept is pretty much the same, we're just copying an object. Next we have, so this is kind of taking care of the memory allocation. One of the questions, if you recall, was how are we actually allocating the memory for our objects? And one variation of the factory pattern is the memory pools. So we allocate a memory pool, and then we have factory methods that are part of that memory pool that allow us to create elements in that memory pool, and then also free those elements. So here, the reason we are using the factory pattern is because we don't want to worry about the allocation of the object. We just want to create an object, and then we want to free the object. So that's the simplification we are adding to our application. We want to have a very simple way to create an object and then free the object, but we don't want to do it. We want to do this allocation in a very particular place in memory. We don't want to do it using the existing memory allocators that are available through the malloc and free, for example. We want to have our own memory allocator there that allocates from a specific data structure. And the simplest way to implement this is if we have just a static array of our elements, and our factory method would then just return the next free element in this array. And if you want to add a little bit more flexibility to this way of just allocating from a static array, you can have an additional data structure which holds a list of free and a list of allocated items, and then you can just take the next item from the list and then put it back when you need to free it. So that's it basically. Best practices of implementing the factory pattern. Have a clear interface. We have already looked at how important it is to have a clean interface. The main point of the factory pattern is to simplify your application. So we looked at the clean interface for shape creation that considerably simplified our application. So have a clean interface to the factory. Make sure that the factory methods are as versatile as possible. One way to do this is to not require that the factory method takes a context parameter, so that it doesn't take a self object as a first argument. That means automatically that the factory is a singleton, and so for different parts of the application, you would not need to pass this context around. Parameterizing the creation in a smart way without limiting the flexibility of the factory implementation. So we can do this with the device tree. We can do this with data structures that hold parameters for creation, but then the actual creation is done by the factory method, which knows about this implementation details of the factory itself. So this is one of the ways to decouple the implementation of the object from the application itself. If we can pass the data in as a separate data structure, basically like a struct, and then the factory creates an object based on the parameters it receives. So that's a good practice as well. Utilizing the abstract API pattern, you will find that you will have to do this if you want to have a flexible way of handling multiple types of objects. And the whole point of the factory is to create abstract objects. So you need to understand the abstract API pattern, and obviously customize when needed, and try to only use a pattern when it makes sense to use that pattern, not just because somebody told you to use that pattern. Pitfalls of the factor pattern, there's basically two of them. Number one is insufficient parameterization, which means that you're not being flexible enough with the creation API. And number two is having too many parameters. So having a too complex API for creating objects. Remember, we're trying to simplify the application. We're trying to decouple the implementation from the application code. That's two goals of the factor pattern. And when implementing it, try to adhere to those two goals. So what are some of the alternatives to the factory pattern? Number one is the object pattern. It's basically, keeping the object creation still visible to the application, but we simplify the creation by basically implementing the object pattern with a proper init and dinit function that handles the initialization of the object. And we can parameterize those functions as well. But the main problem here to understand is that if we go with the object pattern, we don't get the polymorphism that we get with the factory pattern. We cannot easily, change the APIs of those objects. We cannot easily even change the data structure layout, because that would require complete recompilation. So normally this is not a problem that you need to have a complete recompilation, but if you're building applications at a slightly higher level, where you might be dealing with, let's say, shared libraries, then you cannot just change the data layout of data structures, because that would require recompilation. And so you get that automatically with the factory pattern, but you don't get that with the object pattern, because here we know too much about the object. The next alternative is the singleton pattern, where we just don't care about the existence of the object at all. We just have the global functions that don't take any context, that store the context probably as static variables inside the file or somewhere else. This is the most common thing that you see in C programs, and it's most of the time it's not correct implementation. But if you understand the singleton pattern, and if you understand when to use it and when not to use it, then a singleton pattern could be an alternative to the factory pattern, where the whole array of different objects is actually handled entirely by your singleton. As to give you an example, let's say you want to write to a particular endpoint on your network, and the endpoint is described as a string. You can have, if you were to, introduce the factory pattern, you might be creating those endpoints and then managing them inside your application. But if you use a singleton, you could actually have the factory already hidden by the singleton, and then you would just have a method called endpoint submit or endpoint write, and then you would pass just the path to the endpoint, and then the singleton implementation will take care of finding the right endpoint, finding the right object that was previously also created by the internal factory, and then just writing to that endpoint, and so that the implementation is completely hidden from the application. So that could be an alternative sometimes. And the third alternative is the bridge pattern, where we basically hide the complexity in an additional kind of C file or a library that the application interacts with. So we could have basically some implementation that accepts a simple API from the application, and then handles all the creation details for the objects. So that's the third alternative. What have we learned? We have looked at the factory pattern as the primary way of hiding implementation details for creation of objects. We have looked at possible implementation of abstract factories, where we can have polymorphism at the factory level. We have looked at object creation by copy, which is the prototype factory. And lastly, we also looked at object allocation factory, where we can have basically, we use a factory pattern to allocate and free objects. And lastly, here's the quiz. So what is the main purpose of the factory design pattern? Think about it. When would you use the factory pattern? When would you not use the factory pattern? What are the key elements of the factory design pattern? What are some benefits of using the factory design pattern? What are some drawbacks of using the factory pattern? When would you not use it? What are some examples of when the factory pattern is being used in Zephyr? So we have looked at one example, which is the initialization of devices from the device tree. Another example is the memory pools. Another example is the network devices. What are some other examples? Can you find some other examples? In what scenarios is the factory pattern useful for managing creation and lifetime of objects? So when would you use the factory pattern to actually centrally manage the creation and lifetime of objects? How can we easily have a pool of slots from which to allocate objects and manage it in an object-oriented and type-safe way? So we have looked at the simple factory implementation, which shows you how to do this using the container auth macros. Can you apply this to your project that you're working on? What are some of the pros and cons of the factory pattern? What are some of the alternative patterns that you can use when factory pattern may not be a good fit? So thank you for watching this video. I hope you learned something, and I'll see you in the next lesson.